Hey, good morning, future AMPs. Professor Ortiz here. As we're winding down towards the end of the semester, um, I have to say you all are doing great. If you got an email from me asking to meet with me, please respond and provide me 3 available dates and times to meet with me. That will be very important for you to pass this class. There are a couple of you that need to connect with me to figure something out. Just to let you all know that if we do not pass one part or one section, whether it's the lab or the lecture of this class, you're not going to be able to move on to airframe and power plant. It is important that you pass both the lecture and the lab at the same time. This week's lecture is centered on non-destructive testing, maintenance publication, FARs, and TCDs. So let's dive in. A quick and brief introduction of this week's lectures include that the statement that as aircraft increase in complexity, the rising cost of downtime because of growing concern to aircraft operators, airlines could not afford to ground an aircraft for long periods to conduct maintenance or inspections. Furthermore, as components became more expensive and harder to get, new methods of inspections had to be developed to allow inspection without disassembly or destruction of a part. More specifically, it takes time, money, and effort to remove a part. Sometimes you have to order it and you have to wait for the part to arrive, and that takes time, and time is money in aviation. Well, in all aspects of industry in today's world, time is money. The inspection techniques developed are known as inspection without disassembly or destruction of the part. The inspection techniques developed are known as non-destructive testing, or commonly known as NDTs. This chapter will discuss the various methods of NDT, including fundamentals of visual, liquid, penetrant, magnetic, particles, eddy current, ultrasonic, and radiographic inspections. The most fundamental method of inspecting aircraft structures and components is through visual inspection. This method is irreplaceable in certain circumstances and is limited in others. In any case, nothing can be inspected visually unless it is uncovered and made visible by the AMP. Sorry, I'm going to get a little quick drink here. The basic tools required to conduct a visual inspection include a good flashlight, a mirror, and some form of magnifying glass. Those 3 items should never be missing from your toolbox. Flashlights are typically used to give spot time illumination to the inspection area. Some flashlights have flexible extensions that allow you to illuminate inaccessible areas. One of the things that I got when I first started my journey as an AMP is I purchased a stream light. Sure, it's expensive, but I can tell you that I still have that stream light and it still works. And I've dropped it in oil, I've dropped it in ASVAB jet fuel, Skydrol's fallen onto it, inside of it, and that flashlight continues to function. Again, it's a stream light and it comes with a charger. Of course, I'm not sponsored by Streamlight, but there are certain things that are really, really worth mentioning. Also, a good safety wire pliers, like I mentioned in previous lectures. The Blue Point safety wire pliers, those are really, really good. Now, going back to our lecture, a borescope is an optical device similar in principle to a telescope in that it enlarges objects like a magnifying glass. However, a borescope has a small lens mounted on a shaft with a built-in light source that illuminates the area being inspected. Borescopes are typically used to inspect inside engines using the spark plug hole for access. This optical device allows inspections without disassembly. Hence, is the reason why it falls in the NDT, right? Non-destructive testing category. Fiber optic scope is similar to standard borescope, but it has a flexible, articulated probe that can bend around corners. This allows you to view areas deep inside an assembly that previously required disassembly to inspect. In a typical borescope, a bundle of optical glass fiber transmit light from a light source to the scope's end or probe. The probe is then inserted into the structure being inspected, such as the inside of an engine, for example. The maximum length available for a fiber optic borescope is about 4 feet. Special attachments allow mounting of a camera to the borescope and photographically record what is seen through the scope. The picture taken aid in describing situation to an inspector for airworthiness and determination. Similar, a video scope is very similar to a borescope. Is used to inspecting inaccessible locations in the video borescope. The video scope is similar to a fiber optic scope, except that the images is recorded by a tiny light sensitive chip in the end of the probe and transmitted electronically to a video monitor. The video scope provides a high quality image of the area being viewed and can easily be adapted to video recording equipment for inspection, records, and review. You can actually store these on a drive, on a thumb drive, and share it with the management, your leadership team, or with the customer or client. Now, weld inspection. While several means of non-destructive testings are used to inspect welds, visual inspections is the most particular and most common form of visual inspection on a weld. A good weld is uniform in width, with even ripples that taper off smoothly into the base metal. There should be no burn marks or signs of overheating, and no oxide should be formed on the base metal more than half an inch from the weld. Furthermore, a good weld must be free of gas pockets, porosity, and inclusion, like figure 11-5. If we look at figure -5, we see that there are no marks. Let's see here. You see how it's pretty even here? That's uniformity, right? There's no extra material going off to the side, so a bad weld would look something like that. If I can switch the color of my pencil here, a weld that looks like this would actually not be a good weld, right? Because it's not uniform all the way through. So this is really nice here on this side, the butt weld. And also a fillet weld. Look at this side over here. It's perfectly, right? Of course, in this world, nothing is perfect, but we want to get as close as possible. Penetration is the depth of fusion in a weld and is the most important characteristic of a good weld. Penetration depends on the thickness of the material to be joined, the size of the filler rod, and welding technique. A typical butt weld should penetrate 100% of the thickness of the base metal, while a fillet weld must penetrate 25 to 50%. So this is the butt weld here, and what they're talking about 100% is the thickness of the material being welded. Now on a fillet weld, you see how there is about 25 to 50% penetration there. Okay. Had to readjust a little bit here, but moving on with our lecture. Pore welds display certain telltale characteristics. For example, too much acetylene makes the molten metal boil, causing bumps along the center and the craters along the weld's edge. A cold weld has irregular edges and is considerable in variation in depth of penetration, while excessive heat produces a weld with pitting along its edges and along pointed ripples. If a part of cooled is cooled too quickly after being welded, cracks often appear adjacent to the weld. Whenever a welded joint displays any of these defects, all of the old weld must be removed and the joint re-welded. You can see in figure 11-7 some excessive heat causing pitting and pointed appearances on the ripples and so forth, like in A. You can pause the video and take a quick look at this, a closer look. Liquid penetrant inspection. This one's important because you will be working with this more often than not. It could be said or stated that liquid penetrant inspection is a method of non-destructive inspection or testing suitable for locating cracks, porosity, and other types of faults open to the surface. Penetrant inspections is usable on ferrous and non-ferrous metals, as well as non-porous plastic materials. The primary limitation of a dye penetrant inspection is that a defect must be open to the surface. Dye penetrant inspection is based on the principle of capillary attraction. The area being inspected is covered with a penetrating liquid that has a very low viscosity and low surface tension. This penetrant is allowed to remain on the surface long enough to allow the capillary action to draw the penetrant into any fault that extends to the surface. After sufficient time, the excessive penetrant is washed off and the surface is covered with a developer. The developer, by the process of reverse capillary action, blots the penetrant out of the cracks or the faults, forming a visible line in the developer. If an indication is fuzzy instead of sharp and clear, the probable cause is that the part was not thoroughly washed before the developer was applied. Here we have an example in figure 11-8. When performing a liquid penetrant inspection, the penetrant is spread over the surface of the material being examined. Now remember, it is important for you to completely clean the surface before you start your inspection. Magnetic particle inspection. The non-destructive inspection method most often used for parts made of iron or iron alloys is the magnetic particle inspection. In this method of inspection, a part is magnetized and oxidized containing magnetic particles is poured or sprayed over the part's surface. Any discontinuities in the material, either on or near the surface, create a disruption in the magnetic field around the part. A discontinuity is a disruption in a part's normal physical structure that may or may not affect the usefulness of the part. The magnetic particles in the oxidized align with these disruptions. Magnetic particle inspections is used for detecting cracks, splits, seams, and voids that form when a metal ruptures. It is useful for detecting cold shuts and inclusions of foreign matter that occur when the metal was cast or rolled. However, some types of subsurface discontinuities do not produce sharp enough magnetic poles to attract the oxide and form a good indication of the fault. Principles of magnetic inspection. If you recall from previous chapters, when a material containing large amounts of iron is subject to a strong magnetic field, The magnetic domain within the material align themselves with the part becomes magnetized. When this happens, the part develops both north and south poles and line of flux flow in a continuous stream from the north pole to the south pole. If a break occurs within that part of another set of magnetic poles appear, one on either side of the break. Therefore, when conducting magnetic particle inspection, these poles attract the magnetic particles in the oxide, thereby giving you an indication of the break. So what they're talking about here is the magnetic fields and how they can be disrupted. Principles of magnetic inspections, as we just covered, I do want to emphasize that this is NDT, non-destructive testing method, that is very, very commonly used in today's aviation world. Longitudinal magnetism, is the magnetizing current flows either through a coil in which the part is placed or through a coil around a soft iron yoke. In either method, the magnetic field is oriented along the material so that magnetic fields form on either side of the fault located across the material. As we can appreciate in figure 11-12, when a part is magnetized in a coil or solenoid, the lines of flux pass through the material longitudinally. The same holds true if a part is magnetized using a coil wrapped around a soft iron yoke. In both cases, as the flux lines pass through the part longitudinally, faults that run across the part are detected. Methods of magnetization. It is important to take into consideration that ferrous materials can be magnetized in a variety of ways. For example, simply striking a piece of iron can induce a weak magnetic field. However, for the purpose of magnetic particles inspections, magnetic fields must be precisely controlled. Therefore, magnetic particle inspection employs direct current magnetization, half wave rectified DC magnetization, or alternating current magnetization. When it comes to like the direct current, we can say that pure direct current at voltages from 110 to 440 has excellent penetrating qualities and is suitable for magnetizing parts in coil with yokes. However, DC has disadvantages of being difficult to change its value as required for inspecting objects of different sizes. So you have to be able to gauge the thickness of the material that you are testing. Halfway rectified DC. The problem with using pure DC to magnetize parts is that pure DC is not readily available in most shops. However, commercial frequency alternating current is available and can be rectified to DC with a half-wave rectifier. In addition, by controlling the AC input to the DC output can be adjusted to any value. Half-wave DC has the identical penetrating qualities as straight DC, and its pulsating nature helps distribute the magnetic particles so they arrange themselves over any fault. Alternating current. The principle of magnetization is based on the magnetic domains of a material aligning with the external magnetizing force. If the magnetizing force is produced by alternating current, the domain alignment reserves each cycle, thus changing the magnetic polarity. Testing methods. Different types of magnetization procedures must be used for different applications. The two methods you must be familiar with are the residual magnetism method and the continuous magnetism method. The residual magnetism method is when a part is magnetized and the magnetizing force is removed before the testing medium is applied. The part is tested by residual method. This procedure relies on a part's residual or permanent um, inspection. The color of dye used with magnetic particles determines the type of light used for the inspection. If gray, black, or red dye is used, the inspection is made in with white light. However, if a fluorescent dye is used, the part is inspected using black light in a dark booth. The skill and experience of an inspector is a critical factor in determining the effectiveness of a magnetic particle inspection. For example, while faults that are open to the surface are easy to identify, some subsurface faults can be extremely difficult to detect due to the fact that they are strong north and south poles. Now, we also got to consider the fatigue cracks when we're talking about aviation. Flight creates stresses on the aircraft structure. So fatigue cracks, given sharp, clear patterns, generally uniform and unbroken throughout their length. These cracks are often jagged in appearance as compared to the straight indications of seams, and they often change direction slightly in localized areas. Fatigue cracks are only found in parts that were in service. The cracks are usually in high stressed areas of a part where a stress concentration exists. It is important to recognize that even a small fatigue crack indicates that failure is involved with parts is in progress. Heat treat cracks. Heat treat cracks have a smooth outline and are usually less clear with less buildup than fatigue cracks. On the thin sections, such as cylinder barrel walls, heat treat cracks may give very heavy patterns. These heat treat cracks have a characteristic form consisting with the short, jagged lines grouped together. Shrink cracks give a sharp, clear pattern, and the line is usually very jagged. Since the walls of shrink cracks are closely together, their indication generally builds up to less extent than indications of fatigue cracks. Seams. Indications of seams are typically straight, sharp, and fine. They are often intermittent and sometimes have very little buildup. Hairline cracks. Oh, these are very common too. Hairline cracks are very fine seams in which these faces are forced very closely together during fabrication. Hairline indications are very fine and sharp, very little buildup. Discontinuities of this types are normally considered determinal only in high stress parts. Inclusions are non-metallic materials that have been trapped in the solidifying metal during the manufacturing process. Such examples include slag materials and chemical compounds. They are usually elongated and strung out as the material is worked in subsequent processing operations. Non-metallic contaminants that get into the metal or material when it's cast show up as broad and fuzzy as indications. Now, demagnetization of a part after it is inspected is often determinal to its operation of the aircraft. Therefore, before a part is returned to service, it is required to be thoroughly demagnetized. This is accomplished through their AC or DC demagnetization process. In order to demagnetize a part, the magnetic domains must be disorganized. To accomplish this, the part is subject to a magnetizing force opposite to the force used to magnetize it. If the magnetizing force was AC, the domain alternative in polarity, and if the part is slowly removed from a field while current is still flowing, the reversing action progressively becomes weaker. Thus, the domains are left with random orientation and the part is demagnetized. Now, DC demagnetization. AC current does not penetrate a surface very deeply. For this reason, complete demagnetization of some parts require DC demagnetization. To accomplish this, a part is placed in a coil and subjected to more current than initially used to magnetize the part. Current is flowed through the coil, and then the direction of current flow is reversed while decreasing the amount. The direction of current flow continues to be reserved in direction and decrease until the lowest value of current flow is reached. The electronic inspection, the different types of visual inspections that were discussed in Section A and earlier of this lecture, are effective for identifying surface defects and subsurface flaws. In fact, simple inspection techniques are often the most effective. However, many aircraft components are made of non-ferrous materials that must be checked for internal imperfections. To accomplish this, inspection personnel use several electronic inspection methods that provide an electronic view of a component's internal structure. One common, and I think you should get very familiar with this, is the eddy current inspection. When we talk about eddy current inspection, it can be said that that method is a testing method that requires little or no part penetration and can detect surface and subsurface flaws in most metals. Furthermore, it can differentiate among metals and alloys, as well as metals heat treat condition. Eddy current inspection is based on the principle of current acceptance. In other words, it determines the ease with which a material accepts induced current. As AC is induced into the material being tested, the AC measure to determine the material's characteristics. Eddy currents are electrical currents that flow through electrical conductive materials under the influence of an induced electromagnetic field. The ease with which a material accepts the induced current is determined by four properties: its conductivity, permeability, mass, and by the presence of any voids or faults. The conductivity of a metal varies with alloy type, grain, size, degree of heat treatment, and tensile strength. Therefore, an eddy current test can differentiate among any of these characteristics. To perform a conductivity test, a comparison probe and a test probe are held on a reference or sample material, and the meter is balanced to a null indication. Then, when the test probe is placed on an unknown test material, the meter deflects from the null position if the conductivity of the test material is different from that of the reference. Permeability of the material is the measure of its ability to accept lines of magnetic flux. If a bridge type eddy current tester is zeroed with the test probe on reference material, it indicates an off-zero reading when the test probe is placed on a material whose permeability is different from that of the reference. The eddy current meter indirectly measures current flowing in the test probe, and the probe current is proportional to the current induced into the test specimen. The mass of the material being tested determines the ease with which the eddy current flows. When the probe is placed on the surface of the test material and then zeroed, the material moves off the zero when the probe is moved. For example, if the probe passes over an area containing corrosion or some sort of discontinuity, the meter needle deflects, indicating a decrease in mass. However, as the probe is moved over the surface free from fault, it remains steady. One good example that we can use in today's world is the ultrasonic inspection. Is the only form of non-destructive testing that can be used on plastics, ceramics, and most metals. To understand how ultrasonic testing works, you must first understand how sound is produced and transmitted. So this is using sound. If you recall from past lectures, all sound is a product of vibration. When a body vibrates, it produces sound waves that are transmitted by the air surrounding the body. Under normal conditions, these sound waves propagate longitudinally from the source of vibration and are called longitudinal waves. However, a second type of wave propagation occurs at right angles to the direction of sound. This type of wave propagation occurs only in materials made of tightly bound molecules such as solid and are called transverse or shear waves. Shear waves that travel along the surface of materials and do not appreciably extend into the material are known surface waves. Now, radiographic inspection is something that I actually haven't seen too much out there, but I know that some companies, some shops really do use it. So it can be stated that one of the most important methods of non-destructive inspections available in radiographic inspection allows photographic view inside a structure. In other words, this method can use certain sections of the electromagnetic spectrum to photograph an object's interior. Now, I've seen the fiber optics, which we'll talk a little bit more, where you can insert a probe that has an extension of, usually the longest is about 4 feet, but you can drop it in there, and at the tip it's got a camera, and you'll get a digital image. I've seen that, and I'll talk a little bit more about that. Now, gamma waves. They consist of radiation energy produced by the disintegration of very specific chemical elements known as isotopes. An isotope is a form of chemical element that has the same number of protons as normal atoms, but a different number of neutrons. This causes an isotope to have different physical properties since it has a nucleus that is said to be in an excited or metastable state. Now, inspecting composites. Composite structures contain materials that sometimes make non-destructive testing very difficult. For example, many honeycomb structures are metal backed. This renders X-ray inspection ineffective, since an X-ray that will penetrate the metal backing will be too powerful to provide resolution on composite material. In addition, dye penetrant is generally ineffective on a laminated composite structure, since the laminations and weaves of composite material absorb the retains of the dye, much like crack and other defects. However, a number of methods of NDTs are effective on composite materials. The first one is the coin tap test. Although it is one of the most simple test available, the coin tap test also allows most effective on the laminated bonded honeycomb materials to detect structural flaws. With this method, you merely tap the edge of a coin slightly along the area you suspect is damaged. Undamaged material produce a solid ring sound, while damaged areas will create more of a thump. So a thump. I don't have a coin with me, but bottom line is what you're doing is you're getting a coin. You will be getting a coin and you will be tapping. You can hear the different sound. That would indicate, the different sound would indicate that there is something wrong inside the honeycomb. Also, when there are small holes on the surface, water can leak through there, and some of the thump can be generated by water. Also, animals and vermin, squirrels, and all kinds of creatures can crawl inside aircrafts, and create nests and destroy the integrity of the structural parts of an aircraft. I need more caffeine. We need some of that caffeine. Yeah. So as I was saying, the coin tap test will make a hollow thud when areas where there's damage or areas of concern. Thermography locates flaws in a part by measuring temperature variations at the part's surface. A part is heated, and the temperature differences are then measured with an infrared camera or film. Thermography requires a knowledge of the test material's thermal conductivity, which is then compared to a reference standard. So, bottom line is you heat the part, and it's gotta heat at the same rate at the same temperature. If there is a discrepancy, that means that that area is then damaged or an area of concern. Now, radiography is an X-ray, and although X-rays are not effective on certain bonded structures, other type of radiographic inspections can detect surface cracks and internal damage on many composite structures. In particular, radiography can detect water inside honeycomb core cells. Remember, I shared about sometimes there will be a hole, water will leak through there. You can't really see it. You can't hear it because you can't really move a wing. Although you could, if the hole is big enough, you could probably drop a probe in there and see with the camera, you could see if there's water, but that's very difficult. So the X-ray method would be appropriate. Now we're shifting gears. We're going to go into maintenance publication forms, TCDs, and records. So, a quick and brief introduction. Screwdrivers, wrenches, and sockets are some of the tools you use to maintain and repair aircraft. However, another tool that must not be neglected and very much taken into consideration consists of publications and forms that serve as a guide and record for your maintenance activities. For example, a typical transport aircraft contains many miles of electrical wire for indicating lighting and control systems. Attempting to troubleshoot maintenance problems without access to the manufacturer's wiring manual would be frustrating and almost impossible. A thorough knowledge of regulatory publications such as the FAA regulations or the FARs and non-regulatory materials such as the manufacturer manuals is every bit as important as the tools in your toolbox. And how to read them, how to interpret them is part of what we're going to learn today. So the FAA, for more than 20 years after the Wright brothers' first flight, aviation was virtually an unregulated industry. Anyone who wanted could design, build, and fly an aircraft without obtaining approval from the government. Predictably, the safety record of early air transport was not very good, and the government responded by passing the Air Commerce Act in 1926, which required registration of aircraft and the licensing of pilots and mechanics. In 1938, the Air Commerce Act was repealed and replaced by the Civil Aeronautics Act. This law created Civil Aeronautics Administration and Civil Aeronautics Board, which established and enforced all regulations pertaining to civil aviation. So if we think about it, next year, 2026, this effort and regulation will have 100 years. Fun fact. So the Federal Aviation Act of 1958 repealed Civil Aeronautics Act and created the Federal Aviation Agency, the FAA. The agency was brought into the Department of Transportation in 1967 and renamed the Federal Aviation Administration. Currently, the FAA is charged with the responsibility of regulating and promoting civil aviation in the United States. The FAA's powers and responsibility are quite broad, governing virtually every aspect of aircraft manufacture, operating, and maintenance. The primary regulatory tools that the FAA are the FAR's Federal Aviation Regulations. When the FAA wants to adopt a new rule or regulation, it formulates a proposal called notice of response rulemaking, and they publish it in a Federal Register. Comments and suggestions are then solicited from the general public and interest parties. After a prescribed comment period, the proposals are adopted and printed in Title 14 of the Code Federal Regulation, therefore becoming federal law. To help organize, the FARs are broken down into separate sections or parts. For example, FAR Part 65 prescribes the requirement, privileges, and limitations for certification of airmen other than flight crew members, which include aviation maintenance technicians. Copies of the FARs are available from the government printing office or from a number of private suppliers, including a publisher of this textbook. Since the regulations change frequently, all copies must be periodically updated. Repair stations, aviation maintenance training schools, and other affected by the FARs are required to keep their FARs up to date. For your course of study, you may use FAR textbook produced by the government or some other publisher. These publications serve as a good general guide to the content of the regulations. However, when you take your practical test, you must have access to a current set of updated FARs. Maintenance FARs. Many regulations do not affect the maintenance technician and require no discussion. Others, however, are vital importance to the technicians in the performance of their duties. It is imperative for all technicians to be familiar with these regulations and to follow them when exercising the privileges of an A&P certificate. Some of the regulations concerning aircraft maintenance and inspections are listed below. Here, I want you to pause the video for the following two slides. This covers a little bit more of the FARs. So pause here and also pause here, because this will help you get a bird's eye view of what I'm talking about. Now, FAR Part 1, for example, provides official definitions of words, abbreviations, and symbols. These definitions establish the foundation of a technician's understanding of aviation maintenance terminology. A technician can utilize FAR Part 1 to aid personal understanding of the terminology, including differentiating between types of maintenance such as maintenance, inspection, overhaul, repair, preservation, and replacement of parts, but excludes preventive maintenance. And preventive maintenance, simple or minor preservation operations and the replacement of small standard parts, not involving complex assembly operations, defining specific airspeed, marking aircraft instruments, and delineating the tasks associated with major and minor repairs and alterations. FAR Part 21 lists the requirements for establishing and maintaining the certification of an aircraft and components. When an aircraft is manufactured, an inspector determines if it conforms to the model's type certificate. The type certificate lists all pertinent information of an aircraft and accessory design. If the aircraft is in conformity, it is used an airworthiness certificate, signifying that it meets the standards for service. The airworthiness certificate stays with the aircraft throughout its service life and is transferred when ownership changes. However, an aircraft must maintain properly in order for airworthiness certificate to remain valid. To ensure that aircraft perform reliably, the FAA requires that all installed parts and appliances conform to the Technical Standard Order (TSOs), are set of specifications that call for parts to meet certain quality standards. A TSO stamp on a part means that the TSO meets the FAA requirements for manufacturing quality and is approved for installation on an aircraft. If a TSO part is called for by the aircraft manufacturer, installation of the non-certificated item can invalidate the aircraft's airworthiness certificate. The FAR specify that it is the responsibility of the person or agency installing a part to verify that it conforms to the proper standard or TSOs. Therefore, you must make sure that the hardware appliances you install on an aircraft are certified. Companies can obtain a part manufacturing approval (PMAs) from a FAA to produce replacement parts. However, the manufacturer must prove to the FAA that their product meets the performance and quality standards. Again, the installation of non-approved parts can affect the airworthiness of the aircraft and lead to catastrophic failure. Always check parts for TSO and PMA's conformity. Now, FAR Part 23 describes in detail the performance characteristic various aircraft must demonstrate to be airworthy. If it specifies requirements for every component and system installed on an aircraft, often down to the smallest detail, maintenance technicians can use Part 23 to verify the particular aircraft or component is in conformity with its type certificate. For example, when a cockpit instrument are repaired or replaced, the technician installing the instrument must check that the range markings painted on the instrument face are correct. The aircraft's approved flight manual give the correct operation speed ranges for a particular model. Part 23 also specifies the color codes and instrument face markings that must be on all flight and engine instruments. Now here we'll keep it simple for the FAR Part 39 Airworthiness Directive. When an unsafe condition exists with an aircraft engine, propeller, or accessory, the FAA issues an airworthiness directive. It's pretty much like letting people know, you know what, this is what's going wrong with this aircraft. In today's world, we can commonly associate to automotive recalls, right? So when there's a recall on a Toyota Tacoma for whatever, the transmission on second gear, now that same thing happens in aviation, and the airworthiness directive is pretty much like an automotive recall. And they are published in the same basic format with 7 main sections: identification, amendment numbers, statement of applicability, statement of the existing unsafe condition, compliance time, method of compliance, additional information, and the effective date of the airworthiness directive. The AD must be complied with in the time frame given using the described method, which may include inspection, replacement of parts, modification of design, or change in operating procedures. So one common way that the FAA generates or creates an airworthiness directive is if they, for example, there are 4 accidents with the Boeing 777, for example, right, a 777, and every time they landed on all 4 accidents, the right landing gear gave in, right? So now the FAA is going to see a pattern, right? When it lands, the Boeing 777, the right landing gear is collapsing. That is grounds for airworthiness directive. That is more of a simpler explanation. I hope I make a little sense. So repairs and alterations. A repair is an operation that restores an item to condition of practical operation or to the original condition, whereas an alteration is any change in the configuration or design of an aircraft. So if you're changing the landing gear and it's gonna increase the height of the aircraft, that is an alteration. That's not a repair. Okay, a repair would be you remove the landing gear for the Boeing 777 and you replace it with a new but exactly the same type of landing gear. Now, if an airworthiness directive was issued, you're probably not going to be replacing the landing gear with the same type of landing gear because there's a default, there's a recall, there's an issue with that type, even if it's brand new, right? A major repair is one that is that, if improperly done, might appreciably affect weight, balance, structural strength, performance, power plant operation, flight characteristics, or other airworthiness factors. It is also a repair that cannot be performed using elementary operation. A major alteration is an alteration not listed in the product's specification that might affect the product's performance in a similar fashion to a major repair. Now, preventive maintenance consists of preservation, upkeep, like an oil change in your car. That's preventive maintenance, right? A simple replacement of small parts or procedures. Under some circumstances, the FARs allow licensed airmen other than maintenance personnel to perform preventive maintenance. For example, if an aircraft owner holds at least a private pilot license, the owner can, among other things, change an aircraft oil and replace or repair a landing gear tire. A complete listing of those items that are classified as preventive maintenance is given in Appendix A of the FAR Part 43. Inspections checklist. FAR 43.15 lists the performance criteria for performing inspections and specifically states that a checklist which meets the minimum requirements listed as in the FAR 43 Appendix D must be used for all annual and 100-hour inspection. This, however, does not preclude you from developing a more extensive checklist or using one prepared by a repair station or manufacturer. As long as the checklist covers the items listed in Appendix D, it may be used. So you can build on Appendix D just for safety, right? If you want to build more on that list. Now, FAR Part 91 is entitled General Operating and Flight Rules, of which Subpart E contains the regulation governing the maintenance, preventive maintenance, and alterations of the U.S. registered aircraft. Unlike Part 43, Subpart E of Part 91 outlines the inspection that must be performed on all aircraft. Inspection of airframes, power plant, and appliances is the single most effective way to identify potential problems and ensure safe operations. As a result, inspections are one of the aircraft's maintenance technicians' primary duties. The FAA requires aircraft and their associated components to be inspected regularly. The frequency of these inspections depend on the type and use of the aircraft or components. Annual inspections state the FAR Part 91 states that all general aviation aircraft must go through an annual inspection to remain airworthy. All annual inspections are based on calendar months and therefore are due on the last day of the 12th month after the last annual was completed. For example, if a previous annual was completed on June 11th, 1995, the next annual inspection is due on June 30th, 1996. Annual inspections must be performed regardless of the number of hours flown in a various year. Furthermore, they may only be performed by airframe and power plant mechanics holding an inspection authorization. The AI cannot delegate the inspection duties to an airman and power plant mechanic, nor may an AI merely supervise an annual inspection. The 100-hour inspection or general aviation aircraft that are operated for hire must be inspected every 100 flight hours. This inspection is in addition to the annual inspection requirement and covers the same items as the annual inspection. The major difference is that the A&P technician may perform a 100-hour inspection. As in the case of the annual inspection, the person conducting a 100-hour inspection cannot delegate duties to anybody other than another A&P. The operating hours are the primary consideration for determining when the next 100-hour inspection is due. As the name implies, a 100-hour inspection is due every 100 hours after the last 100-hour inspection. However, there is a provision for extending the 100-hour interval up to the maximum of 10 hours to permit the aircraft to fly to a place where the inspection can be accomplished. However, when this is done, the number of hours is in excess of the 100-hour interval are reduced from the next inspection. For example, if a flight to a place where a 100-hour inspection can be conducted takes the aircraft 6 hours beyond the 100-hour inspection interval, the next 100-hour inspection would be due 94 hours. In other words, the next inspection interval is short-ended by the same amount of time of the previous inspection. So what they're saying here is, for example, let's just say that here's the 100 hours, right? But you are still far away from, or the pilot is far away from the repair station, okay? And it takes them 10 hours of flight to get to the repair station to complete their 100-hour, right? So you can complete it at 110 hours, right? But the following inspection, so this is inspection 1. Now the following inspection, you're not going to be allowed 100 hours. Now you're only allowed 90 hours. Okay? Okay. 90 hours for the second 100-hour inspection, the 100-hour inspection. So if you go over the 100 hours, you have to deduct this from the next inspection, because this should have been a 100-hour inspection, the second one, but because you went over, you have to subtract them. The progressive inspection is designed for aircraft operators who do not wish to have their aircraft grounded for several days while an annual or 100-hour inspection is being accomplished. Instead, the inspection may be performed in segments each 90 days or at each 25-hour interval. The procedures for establishing a progressive inspection program are covered by FAR Part 91. And the owner must request this program. Furthermore, approval must be received from the FAA prior to the beginning of a progressive inspection. So if you're using the aircraft like continuously and you don't want to ground the aircraft for a complete 100-hour or annual, you have the option to request permission in writing to do a progressive inspection, which will allow you to do small steps of the inspection every 25-hour interval. Now, if the aircraft has had a history of issues, the FAA is probably not going to approve a progressive inspection. Now, moving forward, we are going to be talking about the ELT, the Emergency Locator Transmitter, which emits a radio distress beacon at 121.5 megahertz when it is triggered by the pilot or by an abrupt deceleration of the aircraft. To enhance the chances of rescue in a case of an accident, FAR 91.207 requires that all U.S. registered aircraft be equipped with an ELT. ELTs must be inspected every 12 calendar months for proper installation, battery condition, and expiration date, operation of the controls and crash sensors, and radio signal strength. This is how a down aircraft is found. Now, there's also the advisory circulars, the ACs. Many of the technical publications and regulations issued by the FAA are complex in nature and often require additional explanation. As a result, the FAA issues the advisory circulars to inform, explain, and provide further guidance. The ACs are informative only and cannot be used as approved data unless incorporated into a regulation or an airworthiness directive. ACs are listed in numerical sequence closely following the same subject areas covered by the FARs. Some of the subject areas are 00 is general, 10 is procedural rules, 20 aircraft, 60 airmen, 120 aircraft carriers, air travel clubs and operators for compensation and hire, certification and operations. Another popular AC within The 43 series is the AC 43.91 Echo, which gives information on how to complete a major repair and alteration form. In particular, it lists FAA approved data source that can be used as a reference for major repairs and alteration. Data obtained from Airworthiness Directorate approved manufacturer's instructions, type certificate data sheet, supplemental type certificates, and technical standard order are considered approved. To improve aviation safety, the FAA gathers information on mechanical problems and difficulties discovered by aviation maintenance technicians working in the field. When encountering a new or unusual maintenance problem, the technician is requested to fill out and mail FAA Form 8010-4, malfunction or defect report detailing the problem. When the FAA detects a trend performing with a particular aircraft, it publishes the information on the AC 43-16 Alpha aviation maintenance alerts. Alerts are issued monthly to distribute the information gathered with the goal of improving service reliability. Now, the type certificate data sheet. As previously discussed, new airframes, power plants, and appliances are issued a TCD once the FAA has approval. The TCD assigns to the product is also used on a certificate data sheet, which lists technical and other information concerning the product. The type certificate number within the date and revision numbers of the data sheet is enclosed in a box located in the upper right corner of the data sheet. Now, an aircraft type certificate data sheet contains the information necessary for the proper maintenance and inspection of an aircraft or its associated equipment. Information contained in a TCDs is considered approved data for use on a 337 form. Any deviation from the items listed in the data sheet is considered a major alteration and must be documented by the major repair or alterations form. I want you to pause here and I want you to go through this sheet briefly, take notes. And then the TCDs are used during annual inspections to ensure that the aircraft conforms to its type certificate. For example, a TCD's list of aircraft's various airspeed limits. These limits must be marked on the face of the aircraft's airspeed, indicating in accordance with the FAR Part 23.1545, and the technician performing the inspection must check these instrument markings to ensure they agree with those of the TCDs, meaning that it's your responsibility to make sure that whatever the reading is on, in the cockpit, the pilot will have the correct reading to make decisions during flight. In other words, you're responsible for all the information that the pilot has at their disposal in the cockpit. The TCDs also contain information required to perform a weight and balance check on an aircraft, which we will cover here pretty soon on the next lecture. For example, the leveling means, locating of the datum, and the center of gravity range are listed in the data sheets and must be used in weight and balance calculations. Here are some examples. I want you to pause again and look at this type certificate data sheet. Get a little familiar with them. I will include them in the supplemental materials for this week. Here's another example. Get familiar with it. Online maintenance publications. The majority of maintenance publications produced by the government and manufacturers are available through the internet. These online publications are updated continually and can be researched, viewed, downloaded, and printed as needed. Microfiche systems are often the norm for technicians performing research and maintenance publications, although in today's world, microfiche is no longer the case. We use the internet, everything's accessible, right? So you'll have that at your disposal. Now, the parts manufacturing approval technical standard order can be stated as the FAA maintains online list of those parts given PMA approval, right? So the website also includes information concerning how to attain a PMA approval. Plus, it provides an index of authorized TSO parts and appliances, canceled TSO, and information regarding TSO authorizations. The type certificate data sheet is used and published for aircraft engines and propellers. The FAA maintains a searchable database of the type certificates. This database can be searched by make, TCD numbers, or product type, or the FAA website. The supplemental type certificates, like type certificates, the FAA maintains a separate database of supplemental type certificates, STCs. Can be searched by STC number, make, office responsible for issuance of the certificate, STC holders, type certificate number, and by product type. The FAA also includes in-depth information that provides guidance for obtaining STC approval, including submission of a 337 form. A discussion of researching and aircraft records for STCs through the file of 337 forms is also found on the STC webpage. The FAA webpage site provides contact information for the STC holder. However, permission to use an STC is not granted through the FAA. Airworthiness Directive. The FAA database of airworthiness directives, or the ADs, provide a comprehensive research tool for every issued AD. The searchable database includes emergency ADs issued in the last or past 30 days, new ADs issued in the past 60 days, and current ADs listed by the make, appliance, and number, as well as the biweekly ADs index. Old and canceled ADs can be researched as well in the history portion of the database. Maintenance forms. As you recall, safety is the primary goal for all aviation professionals. To achieve this goal, the FAA requires thorough documentation of all work performed on an aircraft. Anytime an aircraft is maintained or repaired, an entry must be made in a logbook or a special form. Therefore, you, the A&P, as an aviation mechanic, must become familiar with the forms, certificates, and records that document your maintenance activities and all the work you've completed in order to share that information or pass along to the next individual. Here is an example of an airworthiness certificate. I want you to pause the video. We're almost done. Just take a quick peek at that. And there's also the registration certificate, okay? So I want you to look at that too. So pause the video. And moving on towards the end of this lecture, weight and balance, which we'll talk about soon. Since no two aircraft weigh the same, weight and balance data must be kept with every aircraft. This data must contain an equipment list that identifies the weight and moment of each accessory added to the aircraft. As discussed in previous chapters, any modification or change to the aircraft or its installed equipment requires a new set of weight and balance figures to calculate. Maintenance records. In the past, the historical record of an aircraft and engine operation hours, maintenance actions performed, and inspections accomplished on an aircraft and its power plant were entered in the aircraft and power plant logbook in chronological order, meaning the latest and greatest was at the bottom. These logbooks typically consist of bound volumes of simple forms. Entries were made by maintenance personnel and by the pilot owner of the aircraft. Thank you very much. Again, if I emailed you asking you to connect with me regarding your grades for this class, for the lecture part, please email me back and let's connect. I appreciate you all. Have a wonderful weekend. Take care.